Talking about sequences and series, and first off we're going to define sequences in this lesson. So in Common Core Algebra 1 you studied sequences, which are ordered lists of numbers. So basically just any list of numbers can be considered a sequence. The sequence is formally defined as a function whose domain is the set of positive integers. So the numbers we can plug in for x are 1, 2, 3, and so on. No zeros, no negatives, no decimals or fractions. The domain does not include negative numbers, zeros, or any decimals. The domain also names the position of the term in the sequence. So we're going to connect this idea of a list of numbers to something with more of a function definition. So here's our list. It says this sequence can be represented in the table on the right. So this list of numbers actually goes in the y values. So we already have the 6 here, and 6 is the first number. I'm going to copy down the list in the y's, and then we'll talk about the rest of the x's. Okay. So if I was talking about this list, the second number is 11, the third number is 16, the fourth is 21, and the fifth is 26. So we're seeing basically, if we think of this as a function or represented in a table, the place of the term is the x, and then the value of the term is the y. So this is all explained here. The domain is the position or place of the term, and the range is the actual terms, the y values. Sequences can also be written with function notation. So basically here I have another table to represent that, and then it says subscript notation is used most often. So that's when you start to see things called a sub n. Now when I say that sub, sometimes people think I'm saying like a sub n or something like that. Sub is like S-U-B-N, and it's talking about a subscript or a lower number being represented with the n. So when you say a sub 5, for example, it's very clear that you are talking about the fifth term in the list of numbers. The subscript tells you the position of the term, it shows the domain value. So in this table, with my same sequence, we would call this the a sub n value, so this is kind of being replaced with y. I'm also putting function notation in here with f of n. N is usually the letter that's used for the domain values or the x values because it's the number of the term, the place of the term. So here, I'm actually going to put the places in first. Okay, so a sub 2 is 11, a sub 3 is 16, a sub 4 is 21, and a sub 5 is 26. So those, when I say that a, it's just the letter variable that's used kind of like the f or the function like f of x, and then we write a subscript, and the subscript tells me what number I'm on. So I know that's a lot at once, and we'll be doing a bunch with this, but we're going to start to look at some patterns. Today's kind of like a little bit of everything to get you thinking about everything with sequences. So here are 4 lists of numbers. I would suggest you pause it and see if you can find the pattern in the numbers, find what would be the 6th number in the list, a sub 6, and then you'd leave these last 2 because we'll talk about that next. Okay, so pause the video, see what you can do, and then you can come back. Okay, so here, the pattern in the first list is add 5. Right, each number gets 5 bigger. So if I continued this pattern until I got to the 6th term, or a sub 6, the 6th term by adding 5 would be 31. The next one is a multiplying pattern, and I'm multiplying by 3. 4 times 3 is 12, 12 times 3 is 36, and that would continue through the list. So if I continue this, I'm already up to a sub 5. So if I multiplied by 3 again, that would be 972. So that's a sub 6. My next 2 might be a little trickier to find out. Basically, if I make my first number also a fraction, 1 is 1 over 1. Basically, that numerator kind of counts up with the number of the term I'm on. So if we use that variable n and think about it growing each time, this actually follows a 1 over n pattern. So while it was harder to figure out the pattern, it's easy to find a sub 6 because it's just 1 over n. So that's going to be 1/6 by the time I get to the 6th term. The next one is an easily recognizable pattern of numbers. If you kind of memorize stuff from the beginning of the year, these are the perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. So the pattern here is actually we're taking the number of the term I'm on and cubing it. So when I get to a sub 6, 6 cubed is 216. Okay, so that's just some pattern recognition, something, you even when you were in preschool, you like recognize the pattern of the colors and lists and things like that. So we're just kind of connecting it to some stuff we're doing now and some math notation. So the next section, we're going to read right below, and then that'll let us do the last 2 columns. So this says any sequence that has an adding pattern, and I'm actually going to zoom in a little bit on this. I don't have this smart board. I'm in a different room and it's kind of weird. So here I actually have room to write stuff now. Any sequence that has an adding pattern is called an arithmetic sequence. This type of pattern is the same as what type of function. So when we see a pattern of adding the same number each time, that should tell you that that's really similar to a linear function, except for the domain restriction since it is a sequence. So with linear functions, I can plug in anything I want and I get like a constant line that's connected or continuous. With sequences, we can only plug in 1, 2, 3, 4, and so on because those are the number or the place of the term. The number that is added repeatedly, so whatever we're adding repeatedly has a special name, and we're going to call it the common difference. Right. So looking at my different patterns here, if I wanted to find the one that was arithmetic, since that has an adding pattern, this is called arithmetic. The common difference, what are we adding each time? So the difference here is 5. Any sequence that has a multiplying pattern is called a geometric sequence. This type of pattern is the same as what type of function? What type of function do we repeatedly multiply? That's an exponential function. Except for the domain restriction since it is a sequence. The number that is multiplied repeatedly is called the common ratio. Now, sometimes you use R for common ratio, but since we just used R for the percent change in exponential functions, that would be really confusing to use it for 2 different things. So we're just going to use the B for the common ratio, and that's because it has the same function in our basic exponential equation as this value. So we're just going to use B for the common ratio. So up here, looking through my patterns, here's a multiplying pattern, so that's geometric. My common ratio, what am I multiplying by, is 3. Looking at the other 2, they have nice patterns, they have cubing patterns, they have some sort of fractional pattern, but these are both neither because they are not a straight adding or multiplying pattern. So basically, we wouldn't talk about this at all. They don't have the common difference or a common ratio. So on the next page, we're going to really connect further to those linear and exponential functions. And if you think about how our units relate to each other, it's almost like after unit 6 where we learned basic exponential functions and graph them like 2 to the x, this would kind of go off of that. Unit 7 and 8 kind of went in a different direction off of it. So this isn't like continuing unit 7 and 8, but it's still kind of in that exponential linear area that we were in. So here, since arithmetic sequences follow a linear pattern and geometric sequences follow an exponential pattern, their formulas are very similar to the equations of these types of functions. So that common difference, that number I add over and over again, is really just like a slope, okay? And the common ratio, we're even using the same letter for it, is like the base of an exponential function, what I multiply by over and over again. Now, what's slightly different is when we think about linear and exponential functions, we think about the y-intercept as the starting value. But that y-intercept always has a value of x equals 0, right? Because we're on the y-axis. In a sequence, we don't start with x ever being 0 because there's not a 0 term. We start with x being 1, okay? So when we talk about these type of sequences, when we talk about this type of stuff, we want to start the formula with a sub 1. So it's almost like I'm shifting the formula. So keep that in mind. Very similar to our basic linear and exponentials, but we're going to do a little shift. So we're going to graph this sequence and then work from there. But that's where we're starting from, what I just explained. So here's my numbers. That's the first number, the second number, the third number, and the fourth number. So when I graph these, it's super tempting to just draw a line because that's what it's going to make. But there is no connection between those points. So when I graph this, I'm just going to use a 1-to-1 scale. I have the 0.13, I have the 0.25, 3.7, and 4.9. And that's it. Okay, no connection. If I connected them, it would no longer be a sequence. So my first starting point, even though I might think about talking about a y-intercept being right there, okay, that doesn't really exist. So we have to start with something else. So a sub 1, which is right here, can be thought of a y-intercept that has moved 1 unit in what direction. So when I think about that, if that was a y-intercept, it's almost like I took a y-intercept and I moved it 1 unit to the right. Okay. So it's almost like we're thinking of it slightly differently. It's like we took a function and we shifted it over 1 right, which also should relate to something we've done this year. Okay, so we're going to write the basic form of a linear and exponential function down here. So using all this information and this fact that we're going 1 to the right, we're going to try to put it all together. So our basic linear function, back from the different unit, is just y equals mx plus b. Okay. So now we're going to say, with all those slightly different things, the variables, the notation, all that stuff, how is it going to look different when I write a sequence function? So instead of y, right, we're calling that a sub n. So this is really just, okay, I'm writing notation differently. And instead of x, I'm writing n. So that's just, hey, now we have these different variables, right? Nothing really changed. It's like using a t instead of an x. And, some subscript stuff instead of a y. Now remember up here, if we look back up at the top of the page, okay, we're using difference instead of the slope. So instead of having an m here, I'm going to have a d. Okay. So right now it's kind of weird to have dn, like is that a new word or something, but we're just going to leave that there for now. Now, the next thing I have to think about, and this is the trickiest part, but once you get it, it's like not really like memorizing a new formula, it's just the old one and I moved it over. If I want to move something 1 to the right, in function notation, that change happens in here, and that would be f of x minus 1, right? Because we know it works backwards. Like if it was left, it would be x plus 1, and right is x minus 1. So down here, instead of having an x, I would have an x minus 1. Now, we're not using x anymore. We're using n, so it's n minus 1. So this change from here to here is that shift 1 unit to the right, okay? And then we don't talk about having a y-intercept. We shifted it 1 to the right, so we have an a sub 1 value, okay? So basically, notice something times something plus something, something times something plus something. We changed what we call the slope, we changed the notation and shifted it 1 right, and then we changed this and we're now talking about a start value. So this is your arithmetic sequence formula. Okay, so I don't have an example, but basically the exponential is going to work the same way. And I think it's easier just to say, okay, I did this to the linear, I'm going to do the same thing to the exponential. So first off, our most basic exponential function is a times b to the x. Nothing with like crazy interest or anything like that like we got into in the unit 7-8. So for a geometric sequence, same stuff, right? Y becomes the A7, right? X becomes an N, so it's my exponent waiting for other stuff, okay? Now remember, we're gonna leave B the same, okay? Because I said we're still gonna call this B. We're not changing that, okay? We're gonna shift it over one. So just like here, I had to write N minus one, here I have to write N minus one in the exponent. And then instead of this, remember this represented the y-intercept or the start value. Now we're calling that the new start value, which is that a sub 1, which is the thing that had to be shifted over 1, okay? So those are our two formulas. I could just say, hey, here's some formulas, but hopefully it helps you remember them if you understand that they're just kind of like shifted of something you've done before.